Right. Hello, everyone. This is a technical walkthrough with the project Lighthouse. We're here joined by Michael. Hello, Michael. Thank you very much
Hi.
for joining us today. Michael, if you can, please do a short introduction. I feel like at this point, everyone will know myself. So I'm Tim, responsible for hacker engagement, doing all these technical walkthrough calls. And we're here with Michael from Lighthouse. So, Michael, please take it away.
Hi, my name is Michael. I work on Lighthouse. I've been working on it for about 5 years now. I've worked on lots of different parts of the client, including database stuff, consensus code, slasher, things like this. My role at the moment is kind of mostly as a sort of leadership mentoring role, and keeping Lighthouse sort of running, and keeping it up to date with hard forks that are happening on Ethereum, as well as optimizations and stuff that we want to get in. And it's a very satisfying job. And I'm happy to be here today talking to everyone about security.
Wonderful. Okay, Michael, then let's start. I guess the first major point is just, high-level coverage of the database. You told me before that you have slides, so I guess we can start with them. So please take it away with the functionality and what we can review today.
Cool. I'll just share my screen real quick. Did that work? Yes. Cool. So I think I won't be able to see you, but I can see the slides, so that's something.
I'm no worries.
Okay, good. Let me know if it looks weird or anything. Cool. So Lighthouse is a consensus client for Ethereum. And what this means is it's responsible for Ethereum's consensus layer ever since Ethereum switched to proof of stake, which was in 2022 when we did the merge. So Lighthouse really runs usually as two processes on someone's machine. There's a beacon node, which is the vast majority of our code, which is responsible for connecting to the peer-to-peer network. It's kind of the consensus layer analog of Geth or Nethermind or another execution client that you might have used, but it's what we usually think of as the consensus client is the beacon node. So the beacon node has networking. It has the consensus state transition function, which is defined by the consensus specs. And then it does a lot of validation of messages that it receives from other validators on the network, as well as providing a database for state storage and things like this. So to keep your beacon node running, you just put it in the corner of your house, you leave it on all the time, and it will connect to the Ethereum network and sync with peers and stay in sync. And this is, as I said, the vast majority of Lighthouse's code is related to the beacon node because this is where all the good stuff happens. The other process that we also work on is the Validator Client. So this is a separate binary that you would run. That's actually the same binary, but it's a separate command that you would run alongside the beacon node, only if you are a validator on Ethereum. So Ethereum has maybe 10,000 individuals running validators. Some of those people have multiple validators, staking pools and things like this. And they would run this binary, which is responsible for key management, and then also signing the messages that a validator is required to sign, which we call the duties, the validator duties. So validator duties, the main one is attesting to blocks as they get created. So the way proof of stake consensus works is it's based on voting. And then all of those nodes are validating the blocks, first of all, with their beacon node, and then voting for which block they think is the current best block on the chain. And then they also get to produce blocks, which happens less and less frequently now as the number of validators has grown. But maybe once a year, if you have one validator, you might get to produce a block on Ethereum, which is pretty cool. And as I said, this process is only required by people running validators. So you can just run a full node by connecting to your peers with a beacon node, and you never need to run a validator client. It's only if you're staking ETH that you would run one of these. And the way that the validator client communicates with the beacon node is via a REST HTTP API, which is standardized. So at Lighthouse, we produce both a beacon node and a validator client, which is interoperable with the beacon nodes and validator clients of the other consensus clients, of which there are about 5. So some of those, if you've heard, you'll probably go to the talks for them, like Prism, Teku, Nimbus, Grandine, Lodestar, and maybe a few more in the works coming soon. Cool. So that's the high-level structure. This is a diagram that I had a lot of fun making of Lighthouse, Lighthouse's code base as
It looks very impressive. Just
thank you.
A bit of a
The fonts are maybe a little bit hard to read at this size, and also because I had to export it to PNG, but I've got an SVG version of this that I'll put online somewhere. But this is an overview just of the beacon node. So this is all of the main components. You can see that the purple boxes are internal crates. So a crate is like a Rust package. Lighthouse is written in Rust. A green box is an external crate. So that's a crate that doesn't live inside the SIGP/Lighthouse repo. And then within some of these, I've gone into detail and highlighted specific files that are interesting or important as the sort of rounded edges boxes, and then specific functions with these like arrow trapezium things. And then the external services that Lighthouse communicates with are these ovals here. So it probably makes sense to read this diagram starting from the top. The first thing that happens really is that Lighthouse is connected to a peer-to-peer network. There's a few libraries that interface there. Rust libp2p. So libp2p is the protocol that all of the peers on the network are speaking, and Rust libp2p is the Rust implementation of that we use. And we wrap these two external crates in our own sort of wrappers, one of which is Lighthouse Network, which does a lot of translation between sort of Ethereum specific concepts and the generic, very generic Rust libp2p, as well as into Lighthouse types and things related to our networking generally. And then there's the Gossip sub implementation. This used to live inside Rust libp2p, but the Ethereum implementation has kind of gotten ahead of the spec, and now it lives inside the Lighthouse repo. And then, yeah, tying all of that together, we have this crate inside Lighthouse called the network crate, which is just literally called network. And this is where the message handlers for different types of messages are. We have Gossip methods, which is a file that deals with messages that we get on Gossip. So Gossip is like messages that are just being propagated on the network all the time to everyone. And if you run a beacon node, you're getting these messages in all the time, and you have to handle them, process them, validate them. Sometimes you store them if they're blocks. Sometimes you reject them if they're invalid, things like that. RPC is the process by which you can request a specific thing from one of your peers. So if you see a lot of people voting for a block, but you don't have that block, you can go and request that block from someone. And RPC methods are both the requesters and the responders for those RPC calls. And then sync, which is this, which is the process by which Lighthouse keeps in sync with the rest of the network. So there's algorithms in there for downloading blocks and managing, failures across different peers and things like this. And that ends up being quite a subtle problem to solve. And sync is the place where we solve that. So it's basically a big state machine. Yeah, and then from the networking layer, it will call out into a lot of things from this beacon chain crate in the center here. This is really where a lot of the guts of Lighthouse are. And this is where really important things like block verification, attestation verification, blob verification since Deneb happen. So this is where we are calling out to other crates to do proper cryptographic verification of all the signatures we receive, consensus validation of all of the rules that the specification outlines, enforcing those rules and rejecting things that are invalid, and then as well as sort of importing blocks into the database. This import block function is probably one of the most important in all of Lighthouse, because that's how the chain progresses. After a block is validated, say you receive it on Gossip, Lighthouse will import it and it will go and write it into the database and remember it permanently from that point on. Yeah, some other ones here. Canonical head is what tracks the current head block, as well as caches some information about it. We've got things like the data availability checker, which is a component added in Deneb that keeps track of which blocks and blobs we have all of the data for, or which blocks we have all of the blobs for. There's light client protocol stuff in here. And yeah, lots of other little things. I maybe won't go into detail on all of these because there's a lot here. Yeah, so then branching out to the right here, this is probably one of the other most important areas, is the consensus code. This is where the state transition function is implemented. So the state processing crate here specifically defines what it means for a block to be applied to a state on Ethereum. So there's a specification for this in the Ethereum consensus specs repo. Lighthouse implements an optimized version of that specification in this crate. And we have a lot of fuzzing and testing to make sure that that implementation actually matches the specification. Because if there were a bug here, this would be like the worst possible place for us to have a bug. It would split the Ethereum network. There would be a disagreement about what the state of the chain was, and that would be quite bad. Although thanks to client diversity, it wouldn't be too bad because Lighthouse has about a 32 or 31% share of the network. So we may not even block finalization if we forked here, but it wouldn't be great. Yeah, and then other important components in here. Some of these we've recently released as external crates. So Ethereum SSZ, Treehash, and Millhouse are all crates that we maintain, but which are available separately and are maintained outside of the Lighthouse repo. SSZ is the serialization format. Treehash is how we do hashing of data structures on the consensus layer. And Millhouse is a library that we added more recently, which does persistent data structures with caching. So if you're into functional programming and stuff, go and try and break Millhouse because it's relatively new and also, yeah, quite different from our previous code. It's sort of a more recent idea. Yeah, and then another important component is the crypto over here on the very most far right, and this is basically broken up into three main things. We have BLS, which is the signature algorithm that Ethereum uses, and we use an external library called Blast for that, which I think is the same library used by all consensus clients at the moment, if I'm not mistaken. It's very optimized and very fast. And then we have KZG, which is for doing KZG commitments for Deneb and later. And for that, we use CKZG, which itself depends on Blast. And this just adds a few extra cryptographic primitives on top of the BLS signatures. And then we also use SHA-2 hashing quite extensively. And we use that for Merkle proofs as well as for you're doing this tree hashing. So the tree hashing depends on the SHA-2 crate as well as the Merkle proof crate. Yeah, and that's kind of the main cryptography that we use. But we don't use any SCCP 256K1 particularly or anything like that. Or there's not really much symmetric encryption really at the core. There's maybe for some wallets and stuff. We use that, but mostly it's these three crypto libraries. Yeah, and then other components over on the left here, we've just got, these are some of the more important components that the beacon chain uses. There's, of course, the execution layer, which is, so we have a crate for communicating with the execution client. So in order to run Lighthouse as a beacon node, you need to also run Geth or Reth or Nethermind or Besu or Aragon or something as your execution client. And the two of them communicate via a JSON RPC API. And that's so that blocks get validated both on the consensus level and then also on the execution level. So in order to check that a block is valid, we send it to the execution node and the execution node reports back, yes, this block is valid. And then we also update the execution node and say, okay, this is what the current head block of the chain is. So that all happens in this execution layer crate. The store crate just above that is our database. We use LevelDB at the moment as our main backend, although we are in the process of developing other backends. Yeah, this is relatively straightforward, but there's some optimizations and stuff in there. Pardon me. which we've implemented in order to make archive nodes more efficient, things like this. And that's all in the store crate. We also have the code for communicating with MEV Boost, which is the builder client. It's relatively simple, just make some HTTP requests and caches some payloads and things like this. And then we have the operation pool, which is this component that's responsible for packing consensus blocks. So when you make a consensus block with your validator, you have to include like attestations, any voluntary exits and other messages that might be lying around. And the code that's responsible for packing those blocks as profitably as possible is the operation pool, sort of like the mempool in the execution client. And then the slasher is another component that's pretty much separate. This is the component that it's optional to run, but it will listen for misbehavior by other validators. And if it detects it, will publish proof of that misbehavior to the network so that those validators are ejected. Yeah, and then Lighthouse also has down at the bottom here an HTTP API, which, as I said before, is what the validator client uses to communicate with it. This API is like a REST API as opposed to a JSON RPC API, which we use for the execution client. There's a specification for this that's implemented. You can find it online. Sorry, I'm just going to mute my Discord notifications. One sec.
Or is it all? We all have them.
Okay, I'm good. Yeah, so this API is a REST API, which yeah, there's the specification online for that. The beacon APIs, you can look that up, and we implement everything from that specification. There's also a scheduler down here that we have specific to Lighthouse called the beacon processor, and that sits on top of the Tokyo async library. And that, of course, sits on top of the operating system. Hang on, I might just pause there. Hang on. I'm wondering whether you can see my partner in the background. She just got home, probably. Are you
no worries at all.
I'm doing like, they're like recording a video presentation. We can pause here, but do you want me to go in there?
I don't know.
No, I think I'll go in there just because I think I'll be distracted if you're in the background. Okay, cool. I'll move. Okay, sorry. We can edit
No
this
problem.
out.
Yeah, absolutely. No problem at all.
It can be magic that I just relocate. Cool. Okay, and I'm back. Yeah, so that's I guess that's the main architecture of the beacon node. That's pretty much everything. We can dive into some of this code in a little bit, but I guess I'll just run through a few other slides that I have here. As I mentioned, a very important part of our work is the consensus specs, which are written by other consensus client developers, as well as people from the Ethereum Foundation who work as researchers. And yeah, this is a sort of mapping between parts of the specification and the implementation in Lighthouse. So the beacon chain file defines the core state transition function, which in Lighthouse is implemented in that consensus/state processing crate that I mentioned before. That's the path, that's the file path within the repo. Fork choice is another important component. This is the thing that decides what block is the head of the chain based on all of the votes and attestations by the validators. This has historically been a source of some frustration and bugs, but although we think we've ironed them all out now, but there were specification bugs in this component which caused some long reorgs a few years ago, which was like sort of the talk of Twitter for a few days. And then there's also the P2P spec in P2P interface. And this actually, despite the name, it mostly defines rules for validating consensus messages that you receive on the peer-to-peer network. It's not so much about the peer-to-peer protocol itself, although there is some stuff in there about that. But yeah, these are the block verification, attestation verification, blob verification files that I mentioned before, which are inside the beacon chain crate. Yeah, so in terms of security, Lighthouse has a number of mechanisms to protect itself and protect you as the user running Lighthouse. One of them that I mentioned before is the slashing penalty. So this is a concept in Ethereum where if a validator does something malicious, they get slashed, which means that they lose part of their stake, which is proportional to how many other validators are misbehaving. And then they also get ejected permanently from the network. So if you're staking and you have 32 ETH and then your validator gets slashed, you would lose usually 1 ETH immediately. And then if you're part of a coordinated attack, say, you're going to lose more of your ETH and your validator is going to be unable to continue signing messages, and all of its peers are just going to ignore it, and you'll just basically be kicked off the network. So that's the real like proof of stake security. That's probably the most important security mechanism that the protocol has, and we try and implement that in a way that's as bulletproof as possible, so that basically certain types of attacks are just infeasible, because if you pull it off, even if you successfully pull it off, you lose all of your ETH. So it's not worth doing most of these attacks. And that's like the sort of like a double spend would be a slashable offense. So yeah, you might pull off the double spend, but all the validators that helped you pull it off are going to get slashed. So somebody is losing a lot of money. More sort of, or less reliable than that, we have some other layers of defense, like peer reputation. So a Lighthouse will keep track of which peers are sending it good messages, which peers are sending it bad messages. And if a peer is sending too many invalid messages, which are slowing things down or just getting in the way of proper messages, that peer will eventually get banned. And Lighthouse also prioritizes peers with good reputation over time, which means, yeah, it's kind of a double-edged sword, because if as an attacker you could make your peers behave really well, then you might be able to get in Lighthouse's good books, basically, and then Lighthouse will prefer connections to you, and it might isolate itself from honest peers. And then this is a thing called an Eclipse attack. So the next line is also about eclipses. We have a limit on inbound peers, so that if too many people show up and try and connect to us, we'll say, no, we only accept, maybe 10%, or I don't know exactly the ratio, but we only accept a certain fraction of connections as inbound connections, and we want to find most of our peers through outbound connections. So every now and then, Lighthouse will just go looking for new peers, and it will ask its peers using the discovery protocol, and then it will go and discover and try and keep this diverse set of peers, so that it's not getting a very like echo chamber view of the network, which would be dangerous, because then you're isolated and you can be manipulated and tricked by that eclipse of peers. And then another thing that's come in handy a few times for us, but is also a bit of a double-edged sword, is that we have some fixed size queues and rate limits for messages. So if Lighthouse is receiving heaps and heaps of messages faster than it can process them, these might be messages like attestations from validators on the network, it will queue them, and then eventually, once the queue is full, it will just start dropping them. So this is bad in that we're dropping messages that we should be processing, but it's also good in that it means that Lighthouse doesn't become completely overwhelmed. It doesn't use all of your CPU and RAM and disk trying to process all of this stuff, and it doesn't fall behind necessarily, because it might get blocked for a little while, but it'll drop a bunch of stuff and then be able to catch up once it's processed the backlog. Yeah, I've hinted at a few of these already, but some types of bugs that might exist in Lighthouse, which you could try and look for. The number one, like this would be a guaranteed crit, would be a consensus bug. So if there's a state transition for some block B on top of a state which does not follow the spec, so if the spec says that the the resulting state should be one thing and Lighthouse says the resulting state should be something else. That's a really, really bad bug because this is one that could split the network, and we'd call that a consensus bug. I don't think, touch wood, that there have been any of these in any clients in the last couple of years. I think in the early days of testing hard forks or of testing the beacon chain, we've found a few of these, but as far as I know, there has never been a consensus bug discovered that actually affected Ethereum mainnet. So if you found a bug like this, that's an automatic crit. That's
eternal glory, eternal flame.
It's eternal glory. Yeah,
it's just
yeah. So I'm not saying don't look for them. You know, if that's your thing, go looking for sure. But if you find one, please disclose it responsibly so that we can fix it and so that Ethereum doesn't suffer as a result. Yeah, and then probably the next rung down from that would be a message that, a bug that could stall liveness on the network. So a denial of service bug where you might say, send a specially crafted message over the network to all of your peers, who then process that message, and maybe it causes them to crash immediately, or maybe it causes them to use a lot of CPU and RAM in processing that message. And particularly if that happens without a peer penalty being applied, so that you can keep doing it, or so that you can, you crash a whole bunch of nodes and then they don't even ban you, and then maybe they propagate your messages to other nodes and it sort of crashes even more people from there. That would be quite a bad bug. We've had a few cases where Lighthouse has not applied peer penalties for things that it should, because there's quite a lot of cases, and it's something where you have to carefully consider, okay, well, if someone sends me this, does that mean that they're malicious, or is there some innocent way in which they could be sending this message that appears to be invalid? Because some of the conditions are just don't send me stuff that's too old, and it's well, someone could just be lagging behind a little bit, and that's why they're propagating messages that are old. But it also means that they could be just spamming you with stuff that's old in order to waste your time and waste your bandwidth. So that's one where we did have to add a peer penalty and be a bit more aggressive, because there was a client that was buggy, that was just propagating junk that it shouldn't have been. And we decided, no, we have to ban this client so that they fix their bug, and then so that, anyway, that's a good one to look for. Another part of Lighthouse that's quite complicated is I would say the sync code. I say this because I don't actually understand our sync code. I mostly work on other stuff. But there have been a few bugs in there where Lighthouse has been unable to get back in sync after a certain sequence of events. So if you could find a sequence of messages to send over the network that got Lighthouse into a confused state where it wasn't able to get back in sync, that would be a very powerful bug as well, because you could potentially use that to just target nodes one by one and just shut them off and stop them from following the chain. And then if there are validators attached to those nodes, those validators are going to be taken out of the voting pool for the protocol, which means that you could stop the chain from finalizing, or just reduce the security of the chain, which would not be good. And then another type of bug is we try very hard to avoid having code that will panic. So in Rust, if you panic, it crashes the whole process. That's something that we absolutely don't want to do, basically under any circumstances. So if you find anything that can be sent to Lighthouse to make it crash, that's bad. We would consider that probably a higher severity vulnerability, especially if it can be triggered over the network. If it requires local access or something like this, the same goes for most of these bugs. If it requires being on the same machine as the Lighthouse process, that's much less impactful than if it can be triggered remotely. Remote code execution or remote DOS would be the absolute worst. Fingers crossed we don't have any remote code execution, because most of Lighthouse is written in memory safe Rust, but we do have some unsafe code here and there in some of our dependencies, and we do have C libraries that we use. So I'm not saying it's impossible completely necessarily. In terms of testing, I've listed a few things here which could be good to plug into, or just so you know, like which things are already covered by tests and which tests you could maybe modify or edit or something like this. So for those really spicy critical consensus bugs, to prevent them, we have the consensus spec tests from the Ethereum Foundation, and we have a test runner for those in testing/EF tests. There's also differential fuzzing of the consensus code that's been ongoing for many years now. This is a project maintained actually by us at Sigma Prime. It used to be open source as Beacon Fuzz 1.0, but nowadays it is private just in case it finds a bug, because we don't want that bug to just go out in the wild as like immediately, because then it could be exploited by an attacker on Ethereum mainnet, which would not be good. So unfortunately, we can't share that fuzzing code with anyone, but it does exist and it is running in the background. Recently, I've been working with a colleague of mine as well on doing some correctness proofs. We did proofs on paper, first of all, and then at the moment, he's translating those proofs into formal proofs in Ethereum Prover. We have unit tests all throughout Lighthouse. You can run these tests using the makefile that comes with the repo. There's some end-to-end tests as well inside the repo. In particular, there's this thing called the beacon chain harness, which is good for setting up different testing scenarios, and you can use that to, write very specific sequences of, okay, what happens if this message gets sent, and then this message gets sent, and then this message gets sent, and then you can add assertions and whatever you'd like in there. We have some fuzzing that we did a while ago, which is currently inactive for fork choice. We haven't shared that yet, but we might share that soon. We also have actually, I think this is also private. These last couple of things, we've tried various malicious. We've made various types of malicious nodes. So Mallory is one that sends all sorts of junk, malicious messages at the network level, and then Hydra is one that tries to make as many forks as possible and basically DOS the client by making it process a lot of different forks in parallel, which is a difficult thing for most of the consensus clients. There was a project a while ago where we managed to crash Prism and Teku with Hydra, and then they basically patched so that they are now resilient to Hydra. So at the moment, I don't think any of the clients get crashed by Hydra, but it was an issue in the past. Yeah, okay, I guess this is sort of similar things that we've touched on, but in terms of parts of the code that I think you should look for bugs, sync is quite inherently complex. There's this big state machine. There's lots of different states and lots of different orderings of events that could lead to different states. We are not 100% confident in our testing of this because it gets tested a lot incidentally, but the actual writing unit tests to cover such a large state space is really hard. So yeah, fuzzing this or getting in there and just reading the code and trying to break things could be a good place to start. Another area that could be good to look at is any code that's been added recently. So I gave Deneb here as an example. That was implemented in March of this year, or yeah, maybe February, but it went live in around March or April. So that code is a little bit more green. There are tests and everything for it, but in terms of its interaction with older code, there might be unexpected things which you could look for. And the same goes for the Millhouse library that I was talking about. That was added even more recently in around July or August. So that could be something to look at. Another area that we've struggled with at times is like concurrency and async code. Rust is usually pretty good at preventing bugs at compile time, but there are certain classes of concurrency bug, like deadlocks, that Rust can't prevent at compile time. So we've had a few cases where we've accidentally introduced a deadlock that could be triggered under certain circumstances. So if you could go looking for something that triggers a deadlock or a live lock or maybe a race condition in some cache or some data structure, that would be a really good bug. And yeah, there's a lot of interaction and complexity in like sort of combining async with other concurrency libraries. So we use a library called Rayon, which can crash in certain circumstances, and then Tokyo will also crash in certain circumstances if you do specific things like calling a blocking function from an async task and things like this. Yeah, something that I haven't touched on much is the Validator Client. The Validator Client is generally simpler than the Beacon node, but it does handle some of the most important things like the private keys for the node. So yeah, it could be a good thing to attack in terms of high value payoff if you find a bug. And this is also an area where we haven't. I feel like our current tests are not as comprehensive as I would like, particularly between, like, I mean, the slashing stuff and the key stuff is all very well tested, but the interaction between the validator client and the Beacon node is sort of still a work in progress. I mean, in terms of testing. So yeah, you could go and look at that as a possible angle. And then the last one is dependencies. So Lighthouse has about 1,000 dependencies, I think. The exact number goes up and down a little bit, but yeah, there's a lot of crates that we have in that dependency tree. And we keep track of vulnerabilities in those crates using cargo audit. But if you could find a new or novel vulnerability in one of those dependencies and that's exploitable from within Lighthouse, that would be like a great way to break Lighthouse and yeah, get your foot in the door. In terms of known issues, there are a few things that we would say are not eligible for like a bug bounty just because they're either difficult problems that we are aware of and are working on, or things that are sort of outside the threat model. So we have some known issues with like performance in the Beacon processor. So this is basically the scheduler that decides which tasks to run. And we're aware that our current algorithm can lead to some certain tasks basically never getting run. And we are working on exploring some different scheduling algorithms for that reason. Another one is if the network stops finalizing, then kind of all bets are off in terms of how well the Beacon node will perform, because we're aware that, you know, in a case of non-finality, there can be thousands of chains that we have to sync. There can be lots of data that we need to store on disk. And this is sort of an ongoing project to harden the client against these non-finality scenarios. My colleague, Lion, actually is giving a talk at DevCon at the moment about this exact scenario. And basically, I think all of the consensus clients could probably do better in this area because it's like a worst case scenario that we hope doesn't happen very often or never happens. But it's one that is kind of intrinsically hard to deal with and one that we should develop better tooling around. So that's, I'd say that if you find something around non-finality, it would probably fit under that umbrella. And then another thing that we're aware of is the HTTP API. So Lighthouse's REST API, pardon me, has a lot of endpoints that can basically be used to DOS the node. If you can trigger a lot of work just if you have access to that HTTP API. So our recommendation to users is that they never ever expose their API publicly, just to like the public internet, and that's considered sort of a privileged local access only API, mostly for the validator client to use, or if you're doing analytics or something like this, you should use it locally, but don't like give random people on the internet access to it because they can't use it to crash the node. So that's also a known issue. I've recently uploaded one of the previous security assessments that was done for Lighthouse by Trail of Bits. It was back in 2020, so it's a while ago. But you can go to this link here. It'll also probably end up inside the Lighthouse book, which is part of our docs. These are the, I thought I linked to the book here, but these are the main repos associated with Lighthouse. So the main one is sigp/Lighthouse. Then we have a bunch of Rust crates under the SIGP organization. Rust libp2p, which is the peer-to-peer networking library. That's not maintained by just us. It's also maintained by people from the libp2p Foundation. And then there's the consensus specs and the execution API specs. So these are the specifications for how the consensus layer works, and then how the consensus layer interacts with the execution layer. And in terms of looking at which version of Lighthouse to work on, we develop on the unstable branch, and then the latest release is on the stable branch. So I'd recommend, if you're going to look for vulnerabilities, to look on the stable branch, just because unstable is not necessarily being used by anyone, and it may sort of have bugs that we either know about or are in the process of fixing. Oh yeah, okay. Here's the link to the book. So if you want to learn more about Lighthouse, the book is a good place to start, particularly if you just want to start out running a node, or we have developer docs and stuff there as well. And then I'm very active on Discord as well, along with a bunch of other people from SIGP. So you could join our Discord and chat to us there if you have questions about specific functionality.
We'll also likely invite you to our Discord, like once the competition starts. It'll be a great addition. Yeah.
I'm also on the Immunify Discord as of
wonderful.
So yeah, that's all my slides. I guess
honestly, Michael, that's the most complete presentation so far. Like, I'm speechless, no questions, because you already covered everything, like known issues and everything. I guess one small question, I'm not sure if this was mentioned here. Were there any audits that you had previously, and any, like notable findings in those audits that you may mention?
Yeah. So that prompted me to add this slide, which is the security assessment by Trail of Bits. There were a few things in here that were surprising to us, but nothing that was super groundbreaking. I'd say the one, looking back, it was a few years since I'd looked at this, but there was one that I thought was interesting, where they'd gotten really into the semantics of Rust and found something that we'd not anticipated. So this one about we had a macro that was producing some code that it would substitute into these fields of a struct, and yeah, without getting into too much detail, it was a quirk of Rust where it was not really a well-defined behavior that we were relying on, and they identified that really well. And then we've since, I went and looked at the code and made sure that we fixed it, but yeah, we've since fixed that so that we're not relying on any of this sort of weird, it's not exactly undefined behavior, but it's like underspecified behavior, I guess. Whether, the first field is initialized before the second. That's not necessarily guaranteed. And maybe, yeah, people that have a background in Solidity auditing, I think Solidity has issues or strange sort of language semantics similar to this. You might find, that there are similar things in Rust that you could go hunting for. Yeah, in terms of other vulnerabilities in here, there was nothing particularly impactful. I think the only highs were ones about information leakage, like private keys getting stored in plain text, or a file being provided as a command line argument. And these were ones where I think the outcome was that we just accepted the risk. I think this one we removed, where we had the private key on the actual command line, we removed that. But yeah, basically, in order to run an Ethereum node, at some point you're going to have the private key loaded in memory, and it has to be live there. We do also support now like a thing called Web3 Signer, which helps with that. But yeah, these were interesting bugs that I guess were. Yeah, this one particularly, because it was actually something actionable that we could do, but these other ones were sort of quite heavily baked into the way that everything worked that we couldn't really mitigate them. It's just sort of a risk that we took on board. Yeah.
Understood. Yeah, I think that's a good summary of findings here. That was the only audit done, right? So almost 5 years ago at this point of time.
Yeah, exactly. There was another one done in 2020 as well, but I think we've chosen not to publish that because it was not. Yeah, they didn't find anything basically.
Oh, okay.
Yeah.
Gotcha. I think, honestly, I think we covered all the parts that you already covered all the parts. So the possible bugs, pointing out to the vulnerable areas of the code in your opinion, that's golden. Also the test environment, that test setup, test environment. Um, I'd say, Michael, one last question is, again
Yeah.
from the community, any, central hub of resources where whiteheads can navigate themselves and read more about the protocol, read more about, the structure and how updated those resources are, if any?
Yeah. So I think actually this is a bit of a weakness for us as a team, that we like this diagram I had to make especially for this presentation, and I'm going to add this to our docs, but we don't have heaps and heaps of docs for onboarding new people. I'd say the Lighthouse book is a good place to get started, but it really just scratches the surface of what there is to know about Lighthouse. For a more in-depth guide to the protocol, I would say Ben Edgington's book is hands down the best thing. I think it's eth2book.info. So this book is amazing because it breaks down the consensus specs. So the consensus specs are like the source of truth for how Ethereum should work, how Ethereum's consensus layer should work. And then this book by Ben Edgington basically annotates the spec, takes you through why certain things are the way they are, how the nitty gritty of things work. And this is honestly probably the best resource for learning about the consensus protocol. And it has, not all the sections have been completed, but it has sections on all of the most important parts of the protocol. And I really can't recommend this enough. Like it's the best. Like I look at this all the time when I'm working on Lighthouse. So yeah, it's a great resource.
I see. Wonderful. I think that's going to be enough for now. Plus,
Cool.
of course, the most of the projects under Ethereum umbrella are interconnected. So we're going to have 15 projects participating. You mentioned a few of them already, like Nevermind, Lighthouse, including a bunch of others like consensus layers, smaller layers, and everything. So people will know the code already. They will kind of, check it out here and there, and then of course try to find bugs. For now, Michael, I think that's perfect. I
Awesome.
don't have any more questions. Let
Great.
me stop the recording. And yeah, thank you so much for the presentation once again.
That's great. I'm glad that was what you were after.